All right, so checking out practice homework 7.3. And here's the first problem. And it's actually very similar to the first problem of the last homework with the tractor pulling the lumber. And um, so 7.3 is where we have kinetic energy. So our new equation here, 1 half mv squared. Everything that has motion, velocity, has a kinetic energy. So if something's got a velocity, it has a kinetic energy. And we just talked about work in the last homework. And in here, we're dealing with the work kinetic energy theorem. These are our two big equations for this homework. And remember, the delta symbol is always defined as final minus initial. So having said that, this first problem with the tractor, all this stuff in blue is using the work kinetic energy theorem. And that's why I chose this problem. Like, oh, that's good. They're using work energy theorem. But now that I actually look at the problem, they just want the force here. So that's a little bit unfortunate. And it says if the tractor pulls horizontally and there's a force of friction, so we got our tractor again pulling this sled horizontally, some force applied, and then there's a force of friction holding it back. And it says find the magnitude of the force applied when there's constant speed. So when there's constant speed, when we sum these forces, we have force applied to the right, force of friction to the left gets the minus sign. Newton says this equals ma, but they're telling us a is 0 by saying it's at constant speed. Constant speed means there's 0 acceleration. And so we find that the force applied would have to equal the force of friction. And they actually tell us the force of friction. It's 4,600. And so, well, if the force of friction is 4,600, then so must be the force applied. So, not quite sure what happened there. What's in blue is a good example of the work kinetic energy theorem. In the blue here, you can see they have kinetic energy, and they're using work here. And then this problem just asks for force. So, not quite sure what happened there. But let's check out the next one. If the net work done on an object is positive, what can you conclude about the object's motion? All right. So work is change in kinetic energy, which means final minus initial. They're saying if work is positive, if this is a positive number, then that means kinetic energy final must be greater than kinetic energy initial. Because if this was false, if kinetic energy initial was larger, then we subtract off that larger number, then work would be negative. So if work is positive, that means we're adding energy to the system. We're giving this system energy. And if we're giving it energy, then the kinetic energy must be increasing, must be larger than the initial kinetic energy. So overall, that means if kinetic energy is increasing, and since kinetic energy is 1 half mv squared and the mass is constant, means the velocity must be getting larger. If we look at our choices, first one, object is slowing down. Nope. That would mean negative work. The object is moving with a constant velocity. No, that's not true. Constant velocity would mean work is 0. That's what constant velocity would mean. The object is speeding up is the correct answer. And let's just look at the last one. The object is at rest. Well, it's not at rest. It's moving. So our object is speeding up. That's what positive work is going to mean there. got a baseball leaves a pitcher's hand at that speed. Okay, so I guess this is the pitcher's hand, and here's the ball just leaving their hand. And the mass of this ball is 0.14. And it has a speed. Well, I'm tempted to call it initial. I really should read the rest of the problem before I do that. But that is 29.5. And we're all in proper units there, so we don't need to do any converting. So part A, if air drag is negligible, meaning no friction, how much work has the pitcher done on the ball by throwing it? Okay, so now that I've read the question, this is actually going to be final velocity. So as I said, I was a little hesitant calling that initial, because I really needed to check out what the question was. So they're saying that the ball starts with 0 velocity. So you got your ball in your hand, it's got 0 velocity, and then you throw it. And when you throw it, it gets this velocity. So the initial is 0 because you're holding it, and then you throw it, and you leave your hand, and here is our final velocity then. And they want to know how much work was done. Well, work equals change in kinetic energy, which means final minus initial. So we would have final minus initial. And we do have a common factor here of 1/2 m. And so we could make our math a little bit easier with our calculator by factoring out the greatest common factor there of 1/2 m. And we know initial is 0. And then the final is 29.5. And they're also telling us the mass 0.14. And that answer is 60.9 joules. So that's how much energy the pitcher had to expend to give the ball that velocity. We'll check out the next one. The driver of a car is traveling at that speed. They slam on the brake. The coefficient of kinetic friction is that. Okay? So we have the mass of the car and the people in it is 1,600 in proper units there. And it is initially traveling 27 meters per second. And then they hit the brakes. And then part A said, oh, we also have a coefficient of kinetic friction, 0.75. Part A says, using the work energy principle, so that means work equals change in KE, how far will the car travel before stopping? Okay, well, stopping means the final velocity is 0. So if we look at the work kinetic energy theorem, we have work equals final kinetic energy minus initial kinetic energy. And again, the mass isn't changing, so we could factor that out if we wanted to. Just makes it look maybe a little bit nicer. We know the final is 0, and we know the initial is 27. We also know the mass is 1,600. and this is equal to work. Now, they're not asking for the work, though. They're asking for how far does the car travel? So the work being done is from friction. So this is the change in work. So this is how the work changes. The work is actually caused, though, by friction. We have friction in this problem, and the work from friction, FD cosine theta. Remember, friction opposes motion, and that means the angle will be 180 degrees. Cosine 180 is minus. We have the force of friction times our displacement. The displacement is actually what they want us to solve for. The force of friction is mu kn. And this car is on a horizontal surface, so that means its weight is equal to the normal force. So the force of friction is mu k mg. So looking at our work, we have minus mu k mg and then times d, the distance traveled. So let me put in parentheses, that's the force, the distance traveled, and a minus sign comes from cosine 180. And this work equals that. Oops, I meant my arrow to go up to this one, equals that. I'm going to write that all down. We have minus mu k mgd equals this 1/2 m v final squared minus v initial squared. And we're solving for d. So to solve for d means we'll just divide by minus mu k mg, and then that solves for d. So we would have the mass 1600. And remember, velocity final is 0. So we get a negative velocity initial, so 27 squared, which is 729. And that's all divided by minus mu k, 0.75, times mg, which is the weight of the car. Actually, they don't tell us that. I'm sorry. They do tell us the mass, 1600, and then g 9.8. And that's what I'm going to punch into my calculator. Get 49.6 is the distance traveled. And I'm definitely going to need a new piece of paper. So let's see what the next part has to say. How far would the car travel if we were going twice as fast? Okay, so our new picture is the mass is still the same, but now it's traveling twice as fast. So instead of 27, it's 54. It still stops, and we still have our friction. We have the work is equal to change in kinetic energy. 1/2 mv final minus initial. We know the final is 0 because it's stopping, which means the change in kinetic energy is 1/2 mv initial squared. And work from friction, which I wrote over here again. So friction, mu k mg. And then the work done by friction right here from our last work is minus mu k mg times displacement. So that work hasn't changed. Just because we're speeding up, there's still friction doing its thing. So friction is minus mu k mgd. And we are solving again for distance. So the minus signs will divide out. And if we solve for distance, we get that. And in this case, the masses will cancel. So we can just go 1/2 v initial squared over mu kg. And that answer is $198.4. So the point they're trying to get across here, I would think, is that just because we double the velocity doesn't mean we double the distance. So our previous distance, 49.6, so that's about 50. Doubling 50 would mean 100. But that's not what happened. We actually got almost 200. And that ultimately comes because velocity is squared. So increasing velocity has a lot of effect because you square that effect then, which of course makes it much larger then. So I think that's overall the point they're trying to get across. Doubling the velocity does not mean doubling the distance. Technically, if my velocity is that and I double it, if I double that velocity, doubling it actually results in a factor of 4. And you can see that this is about 50 and this is about 200, which is a factor of 4. Let's look at part C. What happened to the car's original kinetic energy? And what is this car doing again really fast? This is driving. Oh, it's driving and slams on its brakes. So when you're driving and you slam on your brakes, that will cause heating. So your tires get warm. The pavement also gets warm. All the kinetic energy here is being converted, and I'm just looking at the words they're using here. It gets converted into thermal energy, so heating things. If you don't know, temperature is in physics a measure of how fast particles move. So if particles are moving very slowly, you have a very low temperature. And when particles move faster, that's because they have a higher temperature. They have more energy. So the energy from skidding, going into the ground, it's jostling up all those atoms, making them move faster, which increases the energy, the temperature. And so that's what's happening here. The original kinetic energy was converted into thermal by the positive work of friction. Well, friction is not positive work. Friction is always negative work because friction takes energy away. So our answer here is C. And the reason I'm ignoring the other ones is because they don't say anything about thermal energy. They don't say anything about something heating. So our answer there is C. Check out the next one. We got fleas are agile, all right? Wingless insects. There are a lot of context here. Although they are typically that long with that mass, they have an astonishing ability to jump when threatened. Their propulsion, which can briefly produce accelerations more than 100 times that of gravity, comes not from muscles, but in fact from an elastomeric protein called resolin, which acts as a spring. Wow, there's a lot of context to this problem. Given that the typical launch velocity of a flea is about 1 meter per second, what total energy must be stored just before the flea jumps? So they're basically asking, a lot of context here, which can cause confusion. What they're basically saying is if I have my object sitting on the ground and I'm going to jump up, and I want to jump up so that my velocity is 1 meter per second, how much work would that take? So I know there's a lot of context here, a lot of words talking about, fleas and protein. But the simple of it is, we have an object on the ground, and it's going to move up with a velocity of 1 meter per second. Now we have to determine if this is going to be final or initial. This will be final because we're starting from rest, which is 0. So work is change in kinetic energy, final minus initial. The initial velocity is 0 because you start from rest. We're starting from rest, and then we're going to jump up. And so we'd have 1/2 mv final squared. And that's the work done. So they're saying the mass is 4.9 times 10 to the minus 4 in proper units. And we have the velocity of 1 meter per second. So velocity squared, whoops, can't quite see that. Velocity squared, 1. 1 squared is still 1. So our work is 1/2 times m. And half of 4.9 would be 2.45. To the minus 4 joules. And that's how much work, that's how much energy this flea better have to make this jump. Because if they don't have this much of energy ready, they're not going to be able to jump at 1 meter per second. Will jump at a slower speed. And there's our answer. I just want to say again, and trying to make things less confusing if I can, is that there's a lot of words here. A lot of this is just context. Just telling you about a flea, that it can jump, something about proteins. But overall, it just wanted us to know, if we start from rest and jump up with a velocity of 1 meter per second, how much work does that take? And that's our answer. So I just want to say, sometimes I know, or I guess at least, that a lot of words like this can make things sound confusing or look confusing. And I'm just trying to help you see the simple of it. But all those words I do think can cause some confusion. Let's check out the next one. Now, this to me is a much better problem, like what I would put on a test or something. It's just more straightforward and clear. So we have a block of ice that has that mass. And it slides. Oh, it's sliding down an inclined plane. All right. Well, I should have read more of that before I drew my picture. And it slides 0.92. Slides 0.92 meters down. and the slope slopes downward at an angle of 34.4 below the horizon. So usually they give us the one that's above the horizon. So above the horizon means I would draw my angle here, but they're saying below the horizon. So here's the horizon and here's below the horizon. And that is 34.4. And let me just draw this really fast. Let me draw a rectangle. And let me split it into two right triangles. So the angle they're giving us is this one right here. That angle is also the same angle right here. So in other words, the angle right here is also 34.4. And it says, if the block of ice starts from rest, all right, starting from rest means initial velocity is 0, which then means the initial kinetic energy is 0. What is its final speed? So we're going to look at work, change in kinetic energy. We know the, well, I'll just do initial minus, or I'm sorry, final minus initial, because we know the initial is 0, because it's starting from rest. So work is equal to just 1/2 mv final squared. And v final is what they want. They want to know, what is that final speed? So we need to figure out then how to get the work from this block of ice sliding. And it doesn't say anything about friction, so there's no friction there. And there's two ways we can do this. We could first look at a free body diagram. So here's our normal force. Here's the force of gravity. And the motion, our displacement, is down the ramp. So notice our displacement is perpendicular with the normal force. Perpendicular means an angle of 90 degrees. So the work done by the normal force is 0 because cosine 90 is 0. And remember, work is force displacement cosine of the angle between them. And the angle between them is 90. Cosine 90 is 0. 0 times FD is 0. So the normal force, again, not doing any work to push this to the right. However, gravity is now pushing it to the right because we're on an angle. So some of gravity is pushing it to the right. Now, gravity has two components. We have this component here, which is going down. This component does nothing to push the ice. It's this component right here. This component from gravity, this is what's pushing the ice. So if we summed our forces in the x direction, the only force in the x direction is this component right here. This component being the opposite leg of this right triangle. And the angle here is also 34.4. So something I mentioned in class on where to put the angle, if it goes next to this axis or this axis over here, which side does it go on? Think about the ramp closing, so the ramp flattening. As the ramp flattens out, that means the ramp angle goes to 0. If the ramp flattens out, the angle goes to 0. And if you think about over here, if you think the same thing, if the ramp flattens out, that means this arrow is getting closer and closer to this arrow, and it's this angle that's going to 0 as we flatten the ramp. And so this angle is the angle of the ramp. When the ramp angle goes to 0, so does this one. So in the x direction, positive, we'll use an angled coordinate system like this where positive x is to the right. And that component, the opposite component, we'll get from sine of our angle there, 34.4. And that's the only sum in the x direction. It's the only force. Everything else is in the y direction. The normal's in the y direction, and the other component of gravity is also in the y direction. So Newton says this equals ma. And remember, once you have the acceleration, that is the net force. So the net force is mg sine 34.4. And when we have the net force, we can get the total work. Because the total work is equal to the net force times displacement. The net force is mg sine 34.4 and times our displacement. So let me just write that again. Work net is times d. So that's the work. Remember, work also equals change in kinetic energy. So the block starts from rest and then achieves some final velocity, which is what they're actually asking us to solve for. So change in kinetic energy. That is, again, final minus initial. We know the initial is 0 because it's at rest. And so the only change is 1/2 mv final squared. So we have this final equation on the left side and then the right side. And if we look, the masses will divide out. Multiply both sides by 2. And I'm going to bring this d over because it looks a little weird sitting after the sign. And then to get to v final squared, we have to take square root. And there is v final. And we know g. D, they told us, is 0.92. So my calculator says 3.19. And that's the only part. Let's check out the next one. We got two forces of those magnitudes pushing on a box act in opposite directions on that block, which sits atop a frictionless surface as shown in the figure. Initially, the center of the block is at that position. At some later time, the block has moved to the right and its center is now at a new position. So they're giving us a displacement. They're actually giving us a delta x this time. So we have, the delta is always defined as final minus initial. And so x final is 6 centimeters minus x initial, which is minus 6 centimeters. So that gives us 12 centimeters as our change in displacement. And we do need to put this in proper units. So that's 0.12 meters. This is our displacement. And part A says, find the work W1 done on the block by the force F1. So part A is asking, what is the work done by friction 1? What is the work done by friction 1? Well, friction 1 points to the right, and you can see on the picture they have an arrow indicating the box is indeed moving to the right. So our displacement is also to the right. Connecting these tail to tail means the angle between them is 0. So when we look at work, FD cosine theta, theta 0, cosine 0 is 1. So this is just F times D. And they're telling us F1 is 60 newtons. And they also told us the displacement is 0.12. And then my calculator says, force 1, this force from the left pushing to the right, does 7.2 joules during that displacement. So part B. Then now they're asking for how much work is done by force 2. So how much work is done by force 2? So we're using the same equation. However, force 2 is pushing to the left. So there's force 2 pushing to the left. Displacement, though, is to the right. This angle is 180 degrees when we can connect these vectors tail to tail. So cosine 180 is -1. And so we get a minus force times displacement. For force 2, it's 25 newtons. And the displacement is 0.12. And we get -3. Part C, what is the net work? There's two ways. There's always two ways we can go about this. There's only two forces. So to say this again, the normal force and gravity are perpendicular to the motion, so none of them do any work. You can't push down or up to get something to move to the right. So normal and gravity are doing no work. The only things doing work are these two forces, which means if we want to get the total work, we can just add together the contributions of work from all the forces. And we know normal is doing 0 work, gravity is doing 0 work, force 1 is doing 7.2 joules of work, and force 2 is doing -3 joules of work, for a total amount of work of 4.2. 4.2. The other way we could have obtained this is getting the net force. So if we look at the sum of forces in the x direction, we have F1 to the right, F2 to the left. And this equals the net force. So F1 is 60 and F2 is 25. So 35 newtons is the net force. And when we have the net force, we can then look at the total work is equal to the net force times displacement. The net force is 35, and our displacement is 0.12. equals 4.2 joules, as it should, because both of these ways should get you the same answer. So just to say it again, you can either get the net force to find total work, or you can get the total work by adding together all the force contributions. So remember, 7.2 was from force 1, minus 3 is from force 2. The normal force does no work, and gravity does no work. So our answer there for part C, 4.2. And part D, determine the change in kinetic energy. So notice it says final minus initial. That's delta KE. Find a change in kinetic energy as it goes through this motion. Well, no, that work is equal to delta KE. Delta KE is what they're asking for. They want to know what is the change in kinetic energy? Well, the change in kinetic energy is just equal to the total work done. And we just figured out the total work done. It's 4.2. So just to clarify, yes, C and D are the same answers. But just to clarify, we got part C. We got part C by looking at either the net force or summing together all the forces. Whoops, I didn't mean to do that. I meant force 1, force 2, normal force, and weight, where these were both 0. So we can get it through either of those ways. That's how we got net work. And then we know the net work also equals the change in kinetic energy. And that's what they're asking for in part D. What is the change in kinetic energy? Well, that's going to be the same thing as the work we calculated, because that's this equation. That is the work kinetic energy relationship. And that is practice homework 7.3.